Today we're looking at EvoCUA, Evolving Computer Use Agents via Learning from Scalable Synthetic Experience by the team at Meituan. And the big headline here is a new open source state-of-the-art on the OSWorld benchmark. They hit a 56.7% success rate with just a 32B model, which, that blows past the old open source leader, OpenCUA 72B, and it even beats closed weights models like UiTars 2. The real technical breakthrough is the shift from what they call static data scaling, which is basically passive imitation, to evolving experience learning. It's all built on three pillars: a verifiable synthesis engine, a scalable interaction infrastructure that can run over 100,000 sandboxes at once, and an iterative evolutionary learning process. So what this really proves is that active interaction and self-correction are just way more efficient than just piling on more static data.
That's the perfect summary. And we should really break this down because the implications here for agentic AI are just massive.
Right. I mean, everyone is trying to build these computer use agents, these CUAs. We all want an AI that can use a computer like a person. But the paper, it makes a pretty strong claim right at the start. They're saying the current method, this static imitation, is basically hitting a brick wall. Why is that?
Well, it really comes down to the difference between, say, reading a manual and actually driving the car.
Okay.
Most of the current state-of-the-art models, think UiTars or the first OpenCUA, they're trained on these static data sets. You record a human doing a task, turn it into text and screenshots, and you just ask the model to predict the next step.
Which, that works great for language models. You feed it text, it learns to predict text.
But using a computer is a causal loop. It's totally dynamic. You click a button, the whole screen changes, you react to that change. And if you're only training on static traces, the model never gets a feel for that cause and effect. It doesn't learn that its action caused the screen to change.
It's just memorizing a sequence of picture.
Pretty much. And the paper points out this leads to some serious hallucinations when it comes to planning.
How so?
Because it's just doing pattern matching. It starts to invent plausible actions for tasks that aren't even possible in the current state. Or it'll plan out this perfect 10-step workflow that shatters the moment a button is, 5 pixels off. It has no grounding in the environment.
So EvoCUA's whole idea is to move from data scaling to experience scaling. Get the agent to actually live inside the computer.
Exactly.
Right.
But to do that, you need an enormous number of valid tasks. You can't just have it clicking around randomly.
Yeah.
That's where their first pillar comes in, the Verifiable Synthesis Engine.
I really liked this concept they have of generation as validation. I'm usually pretty skeptical when I hear synthetic data for agents. It's often just garbage in, garbage out.
Right. And they solve that by making the data generator also act as a coder. The task architect, which is a vision language model, doesn't just spit out a prompt like sort this Excel column.
Mm-hmm.
It also has to output an executable Python script that can validate the task.
Yeah.
Let's call it $.
Oh, wow. So it's writing the prompt and its own unit test at the same time.
Precisely. And the system immediately spins up a sandbox and tries to run that validator code.
Yeah.
If it fails, a syntax error or whatever, the error message gets fed straight back to the VLM.
And it just keeps trying until it writes a valid task.
Yep. It loops until the validator runs perfectly.
Yeah.
That guarantees every single task in your training set is programmatically solvable.
That's clever. But isn't there a risk that all your data ends up looking too clean, too sterile?
Sure.
Real user desktops are a complete mess.
Oh, absolutely. That's a classic model collapse problem. If an agent only ever sees perfectly generated files, it's going to freak out when it sees a desktop cluttered with, new folder 3 and a bunch of random screenshots.
So how did they dirty up the data to make it more realistic?
They use what they call hybrid resource injection. So first you have parametric synthesis, where they generate the files but randomize all the details, names, dates, the content inside. But then, and this is the key part, they do non-parametric injection.
Okay.
They just grab real, messy data from the internet, random images, super complex PowerPoint slides, audio files, and just drop them into the environment.
So they're literally littering the agent's virtual desktop to force it to learn how to deal with visual noise.
Exactly. You build robustness through friction.
Okay, so you have this perfect curriculum of verifiable, messy tasks. Now you need a place for the agent to learn, a gymnasium. And the numbers they quote here are Well, they're just wild for a research paper. Over 100,000 concurrent instances.
It's the orchestration that's so impressive. You can't just spin up 100K virtual machines. The latency would be a killer. They built a custom asynchronous gateway using something called the reactor pattern.
Which, for anyone who isn't a systems engineer, that just means it's non-blocking. The main controller doesn't have to wait for sandbox number 1 to finish before it talks to sandbox number 2.
Right. It allows for what they call burst scaling. They can bootstrap 10,000 of these environments in less than a minute, and they're running QEMU KVM inside Docker containers. So you get hardware acceleration for the GUI, but you keep the footprint really small.
But the part that I really want to focus on, because I think it's just a masterclass in deep, careful engineering, is the input determinism section.
Yeah.
They actually had to patch the Ubuntu kernel.
This was my favorite part of the paper. It just shows all these layers of abstraction and virtualization, they leak.
Why on earth did they need to go into the kernel?
So imagine the agent outputs a command like press shift plus the less than key. That command has to travel through all these layers. And somewhere in that translation, specifically in the XKB keyboard definitions, weird things can happen. They found a bug where holding shift would actually swap the less than and greater than symbols.
Oh, that's a total nightmare for reinforcement learning. The agent intends to type greater than.
The screen shows less than, and it gets a negative reward.
And it learns that its logic was wrong, even though its logic was perfect.
Exactly. It's just random noise corrupting your training signal. So by patching the kernel, they ensured a perfect one-to-one mapping between the agent's intent and what actually happened on the screen.
And they did something similar with fonts, right? Injecting them into the system cache.
Same exact logic. If a document renders with a different font, maybe the text wraps differently. The vision model sees a totally different state than what was intended.
Yeah.
They systematically eliminated all of that environmental variance.
So the only variable left is the agent's own intelligence.
That's the goal.
Okay, let's get to the training pipeline itself, this multi-stage evolving paradigm. It starts with what they call the cold start phase.
Right. You need to give the model some basic priors about how to behave. You can't just drop a randomly initialized model into a complex GUI.
And they made a really interesting choice with the action space here.
They unified it. It's not just click here, type this. They force the model to output a thought trace before every single action. It has to spell out its goal, its observation, a self-verification, and then a reflection.
It's basically forcing a chain of thought reasoning process into the actual control loop.
And to get the initial training data for that, they used what they call hindsight reasoning. They take a correct sequence of actions, the ground truth, and then they have the model work backwards to generate the reasoning that would have led to those perfect actions.
Sort of reverse engineering the logic to fit the correct behavior.
Exactly. Once you have that baseline, you move into phase 2, rejection sampling fine-tuning, or RFT. This is where that massive infrastructure really starts to shine.
They use a pass at K strategy, but with a twist.
A very important twist. It's dynamic compute budgeting. Normally, you might give every task, say, 10 tries. But they realize that's inefficient, so easy tasks get maybe 1 or 2 rollouts. But the really hard boundary tasks, the ones the model is almost solving, they throw a ton of compute at them to try and find that one successful path.
And once they find that needle in a haystack, that successful run, they don't just dump it into the training data.
No, because even a successful run can be sloppy. Maybe the agent clicked in a blank area, realized its mistake, then clicked the right button. That's a junk step. So they use a judge model to go through and perform step-level denoising to clean it all up.
I thought it was really interesting that they keep the failed runs, too.
They do, but only the reasoning parts. And they label them as failures. It provides a really powerful negative signal. It basically teaches the model, hey, this line of thinking, it leads to a dead end. Don't go down this path.
All of which sets up the final stage, the RL part. They make a strong case that standard DPO, direct preference optimization, is a bad fit for these kinds of tasks.
The problem is trajectory drift. It's huge. In a text chat, if I see something a little different, the conversation can probably get back on track. In a GUI, if I click the wrong link at step 5.
By step 20, I'm on a completely different website.
Totally. So you can't compare the screen from the failed run to the screen from the successful run. They're apples and oranges.
So how does EvoCUA solve that?
With step-level DPO. They find what they call the critical forking point, the $2.
The exact moment the two timelines split.
Yes. The very last step, where both the successful run and the failed run were looking at the exact same screen, but they chose to take different actions. That single moment is the most valuable training signal you can possibly get.
And they introduced 2 ways of learning from that fork. There's action correction, which is the obvious one. You clicked here, but you should have clicked there.
Right.
But the second paradigm, reflection and recovery, that felt like a really big deal.
Oh, it's huge. Because sometimes the right action isn't another click. If the agent gets into a bad state, say a pop-up ad suddenly covers the screen, the preferred action isn't to try and blindly click what's underneath.
The preferred action is to stop.
Exactly. They train the model that in these messed up states, the best thing to do is to generate a reflection trace. The model literally has to output, I am in an error state. My plan is to close this pop-up.
It's like you're teaching it not to panic, to stop, assess the situation, and then recover.
It's so much more like how humans actually learn, right? We learn the most when we make a mistake, pause, and figure out why it was a mistake, right then and there.
So let's get to the results. Does all this kernel patching and critical forking point analysis actually pay off?
Oh, the numbers are just undeniable. The main EvoCUA 32B model gets 56.7% on OSWorld.
And just for context, the previous open source leader, OpenCUA 72B, was at 45.0%.
It's an almost 12% absolute jump with a model that's less than half the size. But for me, the stat that really proved the whole thesis is the 8B model. The little EvoCUA 8B scored 46.1%.
Wait, hold on. The 8B model beat the previous 72B state-of-the-art.
That is the mic drop moment of this paper. It proves pretty conclusively that for agents right now, raw parameter count is not the main bottleneck. The quality of the experience is. A small model that has lived through thousands of these evolved, denoised simulations beats a giant model that just read a book about it.
And they saw efficiency gains too, right? They were solving tasks in fewer steps.
Way fewer. EvoCUA was hitting these scores with a 50-step limit, while a lot of the baselines need 100 steps. It's just more precise. It doesn't flail around.
Did the ablation studies show that one part of the pipeline was the silver bullet?
No, and that's what makes it so convincing. It's a cumulative victory. Adding the thought tokens gave them a bump of about 4.8%. The cold start added another 2.6%. RFT and DPO each added around 3%. You need the whole system. You need the whole gym.
Looking ahead, they do mention one big remaining problem, this training inference discrepancy, and they propose something called STEPO.
Yeah, step-level policy optimization. This gets at the memory problem. During training, we usually let the model see the full, perfect history of every step. But at inference time, to save costs, we usually compress that history into a text summary.
So it's trained with a photographic memory, but then tested with a fuzzy, summarized memory.
Exactly, and that mismatch hurts performance. STEPO is a new algorithm that tries to learn a policy that's robust to that compression, that works well even with an imperfect memory of the past.
And their early results look promising.
Very. It seems to significantly outperform GRPO, which is kind of the standard for this right now.
So zooming all the way out, we've gone through the data, the infrastructure, the training. What's the big takeaway for all the engineers and researchers listening to this?
I think the takeaway is that we're moving from an era of downloading a data set to an era of building a gymnasium. If you want to build a truly capable agent, you can't just scrape more static data. You have to build a rich, realistic environment where the agent can interact, fail safely, and evolve.
It also kind of redefines what a benchmark is. You pointed out that interesting bit in the paper about pass@k.
Right. For a language model, pass@k is about creativity. Can you write this 5 different ways?
Yeah.
But for a GUI agent, the environment itself is noisy.
There's network latency, rendering glitches, random pop-ups.
All of it. So in this world, pass@k isn't about generative diversity. It's about robustness. Can you complete the task even when the window lags for 200 milliseconds? Can you succeed when a font doesn't load?
We're moving from measuring an agent's IQ to measuring its grit.
That's a perfect way to put it.
And for anyone out there actually building these kinds of sandboxes, I really have to say, go read the input determinism section of this paper. The level of detail on the XKB kernel patching is the kind of critical, practical engineering you almost never see in an academic paper.
It's a total hidden gem.
Well, that wraps up our look at EvoCUA, a really fascinating blueprint for the future of agent training. Thanks for joining us.
Thanks for having me.